Hi, this is Garrett McKenzie with Plastic 411. I'm the owner editor of plastic411.com, and today's webinar is on the 15 reasons companies fail at scientific molding. We're going to go into the reasons why, and then we'll also go over ways to avoid those failures. I hope you enjoy the presentation and have a great day. So again, welcome to Plastic 411 training programs. This is the 15 reasons companies fail at scientific molding. So this presentation will cover 15 failures that reduce scientific molding effects. These failures can even cause chaos in a molding system. We're also going to go over historical data, what data needs recorded, and how to use that data in processing. And factor and effect, what critical data best defines changes within a validated process. In addition, we'll also be discussing process solutions. So how to effectively make corrections to return to a state of validation. So first, let's define scientific molding. What is it? So first, let's define what is meant when we refer to a scientific process. So the definition of process is a series of actions or steps taken in order to achieve a particular end. Then we have scientific. Now, scientific is based on or characterized by the methods and principles of science. They're going to be factual and knowledge-based. So when we refer to a robust or scientific process, what we're talking about is a series of actions that lead to a strong and healthy production event. But we must ask, when is a production event strong and healthy? First, we need to look at the 4 primary measurables that define the success or failure of our production operation. We have efficiency, which is the state of achieving maximum productivity with minimum wasted effort or expense. We have downtime, which is mold changes, color changes, maintenance events, and poor planning. We have yield, which is the total parts produced after scrap. Then we also have quality, and when we're talking about quality, we're talking about molded in quality, not sorted in quality. So basically, we want our process to control our scrap. We want 0 scrap. We don't want to be sorting in quality because that puts a risk of affecting our customer and getting bad product to our customer. So when we refer to a robust or scientific process, we're referring to a series of actions that lead to a strong and healthy production event. So why do companies fail? So the biggest reason is reason number 1, the button pushing cowboys. This section is going to go over making adjustments to validated processes. So troubleshooting. What are the key factors for troubleshooting a valid process? We're going to look at historical data because historical data gives us the most information on how a process ran when it was running good. We're also going to look at equipment failures and equipment modification. So if you're making changes to equipment, you can expect a change to the data that you're getting. You can also see a change if equipment is failing to produce in the manner that it normally does. Then we're also going to look at changes in tooling. Any tooling modifications or tooling failures can lead to problems in our process. Then there's also the consideration of material variation. If material isn't consistent, then your process is going to suffer. Then there's also the effect of labors. That's how man or the operator affects our process. Then lastly, we're also going to take into consideration unplanned maintenance. So one of the best ways to avoid becoming a button push cowboy is, first step, you're going to clean the mold. You don't start making changes to the process. You're going to assume that a validated process that's run at minimum of 8 hours, good parts, zero scrap, high efficiency. So you need to figure out what changed. So first thing you do is clean the mold, make sure that it's properly greased, make sure that all mold components are functioning properly. Then you're going to review the process because, like we said, the process has been validated, so we need to figure out what changed. Third step, we're going to review the setup itself. Has something changed in regards to how they set the mold, how they set up components? Then we're also going to look for changes in tooling, such as burrs, buildup, or some broken components. In terms of material variation, we're going to compare whether we change from one lot to another, or are we having a problem with contamination. And then lastly, the labor effect. We need to ask ourselves, is there some way that the operator is affecting our process? We're also going to look at maintenance issues, which a lot of times we're going to use our historical data to identify changes that have happened within the process. So basically what we're talking about is using the 5 M's of molding before making process adjustments. The 5 M's are man, mold, material, machinery, method. Method being process. So no changes should be made before inspecting these components of the molding system. So when we're talking about process troubleshooting, what are the most important tools processors have when diagnosing a changing process? That would be historical data. So historical data is recorded to define the critical requirements of a molding process. So historical data serves as a template for a validated process that has been repeatedly proven to produce high efficiencies with little to no scrap. So when we're talking a validated process, what we're talking about is a process that's run with very little scrap or no scrap. It's producing high efficiencies, and it's run for a minimum of 8 hours. There's really no limit to the amount of historical data that can be recorded. Increasing data collection can only improve a processor's ability to troubleshoot change. So when we're talking about that, it's kind of like comparing a color photo to a black and white photo. They both give you some pertinent information, but the color photo definitely gives you a lot more information about the scene of the picture. So you want to collect that data with the press in good running condition, and you're going to want the mold and barrel temperatures at a running state condition. Process control limits are established to define the requirements for process consistency. Basically, we need to stay within our process windows. Any data that falls outside of the upper and lower control limits are going to trigger a response. That means if we're out of our control limits, then we need to be looking for what changed. So here's a list of recordable historical data parameters. First, we have fill time. Fill time is a measurement of how much time it takes in the injection phase for the screw to reach cutoff position. Injection speed is going to be the primary driver of fill time. Faster speeds decrease fill time, and lower speeds increase fill time. Injection speed also affects injection pressure. Higher speeds equal higher injection pressure, where lower speeds cause a decrease. Now, historical data can be recorded for each stage of velocity through injection profiling. Fill time for each stage is determined by changing the injection speed for each position to 0, starting from the end of ejection to the first stage. Fill time control limits are generally established at plus or minus 0.25 seconds, or 0.5 for the entire window. Another primary process control measurement would be peak pressure. Now, peak pressure is a measurement of pressure reached when, at the end of fill, the screw reaches the cutoff position. Cutting off sooner decreases peak pressure. Cutting off in a lower position increases peak pressure. Now, peak is a primary recordable that should be continually repeatable. Control limits should be within 200 plus or minus. It should be noted that each stage of injection pressure is also a recordable event. Pressures in each of the profiled injection speeds can help to identify changes within the molding process. Now, you're also going to want to record screw recovery time. Screw recovery time is a measurement of time as it relates to the beginning of screw rotate to the end of achieving shot size and decomp after rotation. Now, increasing screw speed lowers screw recovery time, and lowering screw speed will increase screw recovery time. In addition, by increasing your back pressure, it's likely it's going to increase the recovery time, and going down on back pressure can decrease the recovery time. Generally, screw recovery control limits are established at a plus or minus 2 to 3 second window. Next, we have barrel temperature. Barrel temperature is another key measurable. Historical data requires both the set point and actual measurement recording. Now, the reason for including both set point and actual is if there's fluctuations, there's a difference between the set point and actual. You should have that recorded on your process setup sheet. That way, if later on something changes, you know that it's a normal condition, that those two, there's a variance between those two within that zone. Now, controller data would be a minimum recordable. Measurements of barrel temperature between the bands while the press is in a running state with a temperature probe increases the amount of historical data available for analysis. Now, melt temperature is another key measurable that's quite often overlooked. Melt temperature is best recorded with a barrel in a running state. So you're going to want the press to run for a minimum of 30 minutes before recording melt temperature. Your melt temperature should be compared to your SDS. Generally, the material manufacturer will give you information telling you what the melt temperature should be, and generally that would be 25 degrees above or below the melt temperature given on the sheet. So temperatures higher or lower than the established melt temperature during validation can verify changes in the molding condition. Now, melt temperature variations from your own measurement of plus or minus 10 degrees can identify process inconsistencies, and that there may be a problem with the process. Something has changed to cause it to drift outside of validated process control limits. Mold temperature is recorded in both thermolator and hot oil set points versus actuals and steel temperature. Thermolator and hot oil temperatures should be equal in terms of actuals and set points, respectively. Variations are a sign of mechanical failure requiring service. For instance, if a mold set point's at 130 but you're only at 90, it could be that you have a stuck valve, the valve's stuck open, and it's not letting the mold heat like it's probably supposed to. Data is best collected with the press in a good running condition. Mold temperatures should be recorded in a running state condition, and the press should run a minimum of 1 hour of consistent cycles to assure proper heat soak. Process control limits are established to define requirements for process consistency. A normal mold temperature control window would be plus or minus 10 degrees, but it's important to note that process variation can occur in as little as 3 degrees Fahrenheit. Steel temperature is also an excellent way to record, and you do that using a thermal indicator at various measurement locations in the mold. The temps measured as sprue, hot runner drops, runner legs, gate areas, and cavity centers. Those measurements would be recorded on a picture of the mold for future reference. Turbulent flow is another process measurable that you should be taking into account. It's a measurement of GPM, or gallons liters per minute, as it pertains to individual water circuits installed to control mold temperature consistency. Now, these measurements would be taken at both supply and return, and pressure drop can be used to evaluate changes in the molding condition. Turbulent flow can be increased by using smaller water line diameters on the return side. This increases resistance at supply, which causes the water to expand within the water circuits, and it will help to increase turbulent flow. Higher turbulent flow rates improve mold temperature consistency. Mold temperature is a primary driver of process control, and temperature variance leads to process instability. Part weight is another key measurable for identifying process variation. So variations exceeding plus or minus 2 grams can be clear indicators of process variation in smaller parts. Now, this variation is going to be larger for bigger parts, so the best formula to use would be plus or minus 3% either side, so 3% based on the grams of a good part. So part weight establishes that part consistency has been repeated. Lower weights can cause sink or short conditions, and higher weights can be the cause of flash and other overpack conditions. Part weight variation can be a sign of mechanical change. Worn screw or barrel can be verified using part weight variation. Part weight can also be a clear indicator of changes in viscosity as it relates to back pressure. Variations as they relate to regrind usage or lot change variation can improve a processor's ability to pinpoint what has changed. Gate seal is another key measurable that verifies that hot melt at the gate has achieved satisfactory stasis. This assures that material does not flow back into the screw once hole pressure is timed out. Gate seal is measured by part weight. As hold time is added, the part weight increases. Hold time is set 2 seconds higher than the time determined that the part weight is shown to stabilize. So one example of this would be if a part weight is measured and the weight of 7 grams is repeated when the hold time changes from 6 to 7 seconds, then hold time is set at 8 seconds to assure gate seal is consistent. Failure to provide enough time for material waxing can lead to short shots or sink. Too much hold time leads to longer cycles and less profit. If you look at the chart up above, in this comparison between 10 and 12, there's consistent weight. So you'd be best to set the hold time at 12 seconds. Failures number 2 and 3 would be equipment modification and equipment failure. So what we're talking about here is changes being made to equipment or components, and those changes cause a machine to fail. So in terms of equipment modification, validated processes are based strictly upon current equipment, setup, and operation. Any change of equipment, such as auxiliary changeout or machine modification, should be considered suspect. Once modifications or machine replacement has occurred, the potential for process modification is possible. You need to make comparisons to the current validated process and look for variations. If variations exist or process adjustments must be made, the new process must now be revalidated and re-recorded. Auxiliary equipment should be machine specific. When you're using multiple units, such as hot runners, thermolators, hot oil units, etc., and swapping those from one press to the next, well, then you're likely going to see variations to your process. Next, we have to take into consideration equipment failure. Poor performance of machinery can be another contributor to process variation. Set point and actual data can be the key to analyzing poorly performing equipment. For instance, barrel temperature inconsistencies might be a sign of bad heater bands or thermocouple failure. Temperature variance in a thermolator application can identify stuck open valves or valves stuck closed or heaters failing. Cushion can be used to identify check ring failure or barrel wear. Failure to maintain consistent cushion will likely lead to poor process control. Now, screws should, at a minimum, should be checked once every 6 months. The screw should be pulled, and both the screw flights and the barrel should be checked in terms of dimensional capacity. They should be compared to the print offered by the machine manufacturer. Manual measurement of dryer supply and return lines can help identify dryer failures as long as historical data for the normal operation is recorded. A drop in actual supply line temperature can identify heater failure. A drop in return line temperature can reveal signs of poor recovery of heat pulled from the dryer supply. The next 4 reasons are the pillars of process control, and those are heat, pressure, cooling, and time. Heat is one of the primary measurables as it relates to plastic processing. Temperature variability and higher or lower actuals can affect our ability to maintain process consistency. Mold temperature is driven by material temperature, turbulent flow, and water flow rates. Key drivers of barrel temperature are shear heat and the barrel heater bands. Shear heat is responsible for 70 to 90% of barrel temperature, and shear heat is produced by friction in the barrel as pellets are converted from pellet form into a melted state. Heater bands themselves are primarily used to control the heat that is ultimately produced by shear heat. Increasing back pressure drives more material into the barrel. This increases the amount of shear heat. By lowering back pressure, it has the opposite effect. You'll have less material in the barrel and less resistance, therefore less shear. Pressure is number 2, and it's another primary control variable. Pressures are measured during injection, at cutoff, and during the hold stage. Pressure during the injection stage is controlled by injection speed. Faster speeds cause higher pressures, whereas slower speeds lead to lower injection pressures. Peak pressure is controlled by cutoff. Peak can also be affected by changes in material viscosity. Viscosity change is directly related to temperature change. Higher melt temperature reduces viscosity, thus causing a decrease in peak pressure. Lower melt temperatures result in higher viscosity, causing an increase in peak pressure at cutoff. Part weight is also affected by pressure. Increases in pressure will raise part weight. Decreases in part weight are achieved through lower injection or peak pressures, also lower hold pressure. Time is the third primary in the 4 pillars of a successful processing foundation. There are multiple time parameters that not only serve as set points, they are critical process monitoring considerations. Key time measurements would be cycle, fill, recovery, and hold. Cycle defines profitability. Failure to meet quoted cycle not only hampers profitability, it can also lead to changes in dimensional requirements. Inconsistent cycles also lead to process variability. Cooling is the fourth primary in the four pillars of a successful processing foundation. There are multiple cooling conditions that can adversely affect or benefit the overall scope of a validated process. They are critical process monitoring considerations. Key defects that can be caused by cooling time would be long cycle time, warp, dimensional failures, sink, injection marks, or even sticking parts. Cooling also affects profitability. Long cool times in a process leads to long cycles. This increases job runtime and decreases machine runtime. So how do these four things lead to failure? Well, in terms of pressure, changes occur that have a direct relationship to pressure, such as peak pressure, hold pressure, back pressure, or clamp pressure. These changes can be either process or mechanical in nature. The correct approach, you want to look for what changed. Validated processes don't change, conditions do. The wrong approach would be to make process changes without reviewing historical data for change. Also, failing to record all historical data when the press was in a good running state. In terms of time, changes occur that have a direct relationship to pressures such as cycle time, screw recovery time, or fill time. These changes can be either process related or mechanical in nature. Correct approach, you're going to want to look for what changed. Again, validated processes don't change, conditions do. The wrong approach is making process changes without reviewing the historical data. So in terms of cooling, changes occur that have a direct relationship to part cooling, such as warp, part sticking, dimensional shrink. Again, these changes can be either process related or mechanical in nature. And as you see, there's a pattern developing because the correct approach is to look for what changed. I cannot say this enough times. A validated process does not change. Conditions change. So the wrong approach is making process changes without reviewing your historical data. Another way of failing is to fail to record all historical data when the press was in a good running condition. Reasons number 8, 9, and 10 deal directly with the mold itself failing. These are key reasons tooling approach leads to process system failures. One of the first failures in terms of tooling is water setup. Too often, poorly performed mold changes can be the primary cause of changes in the process system. Molds can be watered incorrectly, hoses can be routed differently, or presses are ran with the water turned off. You want to make sure that water schematics are saved for employee reference. This will help to prevent setup failures. Take pictures of the watering procedure and give your deciders very specific instructions in terms of the required procedure for each mold. You also want to make regular comparisons of GPM data. If a mold starts to show signs of reduced turbulent flow, flush the tool with a descaling solution to return the water circuit to a regular flow condition. Poor hot runner setup can be another reason for changes occurring in a validated process. The hot runner is an extension of your nozzle through the mold for direct injection into the cavity. You want to make sure that there are schematics mounted on the mold for employee reference. This will help prevent setup failures. In addition, you want to watch for poorly performing zones. Zone temperatures should stay steady, only wavering 1 to 2 degrees above or below set point. So if you're looking at a set point of 500 and the actual is at 430, well, it's possible that the card itself is performing poorly and you might have to swap cards. Another cause that might cause problems is if you have a pin that's pushed in on a cord and you're not getting a good contact to give heat. So basically you want to make sure that the cables, plugs, and controller connections are all in good condition. Repair or replace components that are in poor shape or not working. Locks for plugs should be kept in good condition to ensure that the plugs are locked into proper state. Poorly performing mold components can be another reason for changes occurring in a validated process. Parting lines wear, vents splash out, components get damaged or break. You want to make sure that before any changes are made, you do a thorough inspection and cleaning of the mold. You're going to want to inspect and lubricate leader pins, slides, and all mating surfaces. Watch for wearing or broken components. Also want to inspect the mold for leaks, both external and internal. Look for metal shavings, gas buildup, and check functionality of all moving components, including cord and valve gates. You're also going to want to inspect the mold to make sure that there isn't any flash that's been stuck into a component and is possibly creating a flash condition. Number 11 is process control. In this section, we're going to discuss establishing upper and lower control limits and monitoring changes within a validated process. So in a nutshell, a robust process has been validated as profitable and repeatable. Following validation, a snapshot of sorts is taken through process recording of all set points and monitoring actuals. This will help to assure that the next time a press is set up, the process can be repeated. Now, once a process is validated, process monitoring is key to measuring for change. Fill time, screw rotate time, cushion, peak pressure, etc. quickly identify changes within the molding process, and they are reliable identifiers to rely on when troubleshooting system changes. Verify all key monitoring measurables. And if you identify that there's a significant variance, use that change to identify what changes might have taken place. Staying within the upper and lower control limits established are the keys to maintaining process control. Normal process control windows are as follows. Fill time would be plus or minus 0.1 seconds. Screw recovery time would be plus or minus 2 to 3 seconds. Cushion would be plus or minus 0.05 inches or 1 millimeter above or below. Peak pressure is plus or minus 100 psi above or below. Melt temperature would be plus or minus 10 degrees Fahrenheit, and you're going to want to use a probe, not a laser. You're also going to want to pay attention to part weight, and as we discussed earlier in the module, part weight varies based on part size. It's generally 2 to 3% above or below. Failure number 12 would be a quality system as it pertains to scientific molding, and we're going to go over reasons a quality system can lead to a processing nightmare. Quality system failures can be another reason why companies fail at scientific molding. You want to remember to make sure that quality failures are not misdiagnosed. You're also going to want to check part dimensions and aesthetics to the print and customer requirements. You need to make comparisons between the last shot previous ran and the first shot from the new run. Whenever possible, you want to utilize the fit to function principle, and it's good practice to compare to engineering samples from the beginning of the product launch. Unnecessary process changes can be just as detrimental as trying to adjust for false defects. So don't be afraid to review historical boundary samples prior to making process changes. Next we have lucky number 13, which would be material failures. We're going to discuss lot-to-lot, regrind, contamination, and moisture. So in terms of failures of material, it's important to understand the effect that material can have on process consistency. Molders need the ability to trust that the materials they are receiving are consistently produced and handled. For instance, we know for a fact that one nylon is not the same as another. They may perform in a similar fashion, but one material response can be totally different despite the base similarities. A process is established based on each specific manufacturer blend. Every time a material lot change occurs, regardless if the material manufacturers insist they are the same, it should be treated as a brand new material and a brand new processing approach. Every time material changes, it requires a totally new process, regardless of whether the material supplier says yes, it is the same compound but better cost. Lot to lot, materials should process the same, but if something changes during a production run, view a different lot of material as suspect. Regrind is another key in process variability. If regrind is to be used, the ratio of virgin and regrind needs to be consistent. Generally, I recommend that you work with an extrusion source to blend your regrind with base. The mixture would then be repelletized. Repelletized materials may require their own unique process when run. Moisture can be another key factor that can lead to unwanted process change. Processes get changed trying to get rid of splay when the real problem is the material is wet and needs further drying. Be sure to have a moisture analyzer in-house to check material moisture properties. You also want to inspect all aspects of the material handling operation. Make sure filters are being cleaned, loaders are functioning properly, products are not being moved improperly, causing damage. Number 14 would be maintenance. We're going to discuss the difference between planned versus unplanned. Maintenance, you want to review press and auxiliaries for changing conditions and poor performance. Machine valves wear, dryers malfunction, carriages get out of alignment, screws wear, and check rings crack or break. Learn to identify equipment failure using monitoring data, and work with your maintenance team to analyze potential faults and get their input into the best approach to fix them. Remember, planned maintenance events are always much more cost-effective than an unplanned repair. Develop a strong preventative maintenance approach to reduce scrap and troubleshooting events. Keep a maintenance log. The log can be used to track machine repair, and then the dates from those repairs when they are repeatable. You can use that to establish frequency of when preventative maintenance events should occur. Lastly, we have number 15, robots and automation. We're going to discuss how automated equipment can lead to process adjustments. Never want to rule out a robot as a potential cause for part defects. Programming and even end-of-arm tooling can cause defects such as drag, pulls, scratches, etc. Inspect parts prior to and after robot extraction to verify that the robot event or the scrap event is robot-based. Similar to robotics, never assume that automation can't be the root cause of a defect event. Inspect the parts prior to and post-automation assembly to verify that scrap issues aren't being caused by poorly performing or maladjusted automation equipment. So these were the 15 biggest failures that occur while trying to practice a systematic approach toward scientific molding. The foundation of scientific molding theory is standardization and monitoring of your operation. This removes chaos from each molding system by simplifying procedures and establishing a concrete molding approach. Lean molding requires consistent replication and thorough documentation of successful runs to assure each production run event is successful. Standardization, monitoring, and maintaining process consistency are the keys to a strong molding foundation and solid profits. We've reached the end of this presentation. I'd like to thank you for your support of Plastic 411. If you have any questions about this presentation or any questions in regard to sanctions, feel free to contact me as listed here. In-plant training.
A database, can you help? I found a four-leaf clover. A database, once you knew yourself, but now you're getting older. You're not afraid to be seen hanging out in the cool part of town. Like you told me, yeah, it was never in doubt. If you were dragging